Thank you very much for the introduction, and we have to escape first, I see. I would like to thank you also for the kind invitation to this beautiful congress. It's quite large and diverse, a lot of heterogeneous catalysis, and if you look around in the world, then we see a lot of polarization. I would like to do the opposite. I would like to make connections, and therefore I gave my lecture the comfortable title, Bridging the Gap Between Homogeneous and Heterogeneous Catalysis. So in our group in Amsterdam, we are looking at developing new tools for transition metal catalysis using supramolecular chemistry. And over the years, we developed supramolecular ligands, supramolecular substrate orientation, catalysis in self-assembled confined spaces or larger nanostructures, and supramolecular strategies in artificial photosynthesis. To give you a bit of a flavor of that, so here you can see our first supramolecular bidentate ligand that forms by pyridine coordination, bringing together a phosphide and a phosphine. And here you see hydrogen-bonded analogues. And the power of this concept is that with a limited number of ligand building blocks, you can make large, diverse sets of catalyst libraries. And this is currently explored by the INCAT company for commercial applications. So here you have an example of supramolecular substrate orientation. In this particular case, we looked at selective orthoborylation, which is typically going for the para or the meta substitution. But if we do substrate orientation by hydrogen bonding, we fix the substrate at a certain position at the metal center, and then we get mainly the orthoborylated product, and we extended this concept to hydroformylation, hydrogenation, and etc. And here you see a few of our beautiful catalysts in confined space. So single catalyst in confined space for hydroformylation, for cyclization reactions, for proto-reduction catalysis. And these are two of our larger nanostructures. And on the menu for today is the question, can we use these cages for controlled synthesis of nanoparticles? And if you look at the development in heterogeneous catalysis, as an outsider I have to say, maybe it's an oversimplified picture, but what you see over the years is that the reactive particles become smaller and smaller, and nowadays single atom catalyst is a very hot topic in this area. And for me this is a little bit strange, because in homogeneous catalysis we typically use a single metal catalyst. So we have been working on this already for years, if you like. But now we would like to answer the question, can we use homogeneous catalysis and coordination chemistry to go up again, so the other direction, with the ultimate goal to have higher control over the nanoparticle that you form. But before I go there, I would like to give you a brief introduction on how we use these type of MNL2N type nanocages. And this is a field that is pioneered by Makoto Fujita, who is making these beautiful structures, so he's really the initiator of the coordination chemistry of this. And here you can see a few examples where you have ditopic pyridine building blocks, and if you add a palladium or a platinum precursor, you can form these nanocages in effectively quantitative yield. And here you just change the angle between these two. And we use these to functionalize them at the inside. And if you functionalize them at the inside, you can pre-organize metal complexes at the core of these nanostructures. So you get very high local concentrations of whatever you put inside. And we wanted to ask the question, can we generate new reactivity with these high local concentrations? Can we do pre-organization of substrate and catalysts in nanospheres? And can we facilitate dinuclear pathways? And I will give a few examples of this before I go to the nanoparticles. So the first example was work done by Raphael Gramage. He is now in Rennes, and he functionalized a ditopic building block with this gold chloride complex. And by adding the palladium precursor, you get this assembly of 24 metal complexes at the inside. And you can estimate the local gold concentration, and that is about 1.1 molar. And if you benchmark that against the concentration of toluene in pure toluene, that's about 9 molar. So from that you can estimate that this is really a high local concentration of gold. Basically a unexplored area in catalysis, extreme high local concentrations. So what we do, we make these nano cages with high local concentrations of gold, but the overall concentration in the flask is just typically millimolar to micromolar. So this means that we can still have high turnover number with respect to the substrate that we generate. And as a first example, he looked at the cyclization of this allyl alcohol to form this 5-membered ring, and we plotted the relative activity as function of the local concentration, because we can dilute by mixing in building blocks. And as you can see, the higher the local concentration, the higher the reactivity. And we think we understand that because at this 1 molar local concentration, we get gold-gold interactions, and therefore the active species is a di- or multi-gold complex. So next we thought, okay, it's quite tedious to make new cages each time you want to change the catalyst. Can we also do this in a supramolecular fashion? So Chichang Wang, he's now in Beijing, he developed this ditopic building block with a guanidinium hydrogen bonding site. And if you add palladium or platinum, you get these cages, nano cages, with 24 of these guanidinium hydrogen bonding sites at the inside of this molecular nanostructure. And these guanidinium binding motifs are known to strongly bind to sulfates because it's ditopic binding, and we established that binding of this sulfonated gold chloride complex is very strong, so association constants are over the 10 to the power 5. And we can upload as many gold complexes as we want, up to 24, which is the maximum, and then you have the proper stoichiometry between the two. Interestingly, you can also use substrates that have a binding motif, and this binding motif is a carboxylate, and carboxylates bind as well, but they bind monotopically, so they bind more weakly. So we have a situation where we can bind strongly a catalyst by supramolecular interactions, and we can pre-organize our substrate to the remaining binding sites without kicking out by competition our catalyst. And if we then do this cyclization reaction that is catalyzed by this gold complex, then you can see here all the control experiments, and here is the kinetic curve where we take advantage of the pre-organization in the cage, and we find turnover frequencies that are 12 to 40 times higher than without pre-organization. So it's just a substrate pre-organization effect over here. We can also play a little bit with substrate selectivity, with a vision that maybe later in complex mixtures we can have control over reactivity. And here we mixed in a substrate that can bind with a substrate that cannot bind, that in the control experiment are converted in a similar fashion. But if you put your catalyst in this nanosphere, then only the substrate that binds is effectively converted. So you can use this cage for multiple tools if you like. Next, we also looked at can we use this to, on purpose, facilitate reactions that operate via dinuclear mechanism. And we found this catalyst, this copper xanthos catalyst, and we did all the kinetics, and we did mass spec analysis in situ, and we did deuterium experiments, and on the basis of that, we figured out that this is the mechanism where we have a pre-equilibrium before the rate determining step, and therefore we have a second order in copper complex. And if you have a higher order in metal complex, you expect if you pre-organize it, you generate a local high concentration, so the reaction should go faster. And this is exactly what we observed. So we redesigned the catalyst by adding sulfonate groups so it can be bound. So this is 6 complexes bound in the cage, and we can bind up to 12 according to our NMR experiments. And then we tested that in this cyclization reaction, and here we have a graph where we change the copper sphere ratio, so the amount of copper catalyst effectively loaded in the cage versus the rate. The overall copper concentration is the same in all experiments, and you can see that by just pre-concentration, you can increase the reaction rate by an order of magnitude on the basis of a rationale based on the mechanism. Okay, so this is a sort of introduction, so you know, you have a little bit of a feeling what type of systems we are working with and we are experienced with. And then the next question is, can we make nanoparticles with atomic precision using these nanospheres? And I realize this is a very challenging question, and I'm not sure we're going to address it today, but that's a cliffhanger. So if you look at nanoparticle formation, you start typically with a complex, you have a nucleation and then a growth, and in the growth phase you can have surface-seeded growth, you can have agglomeration, and you can have Oswald ripening. And if you think about pre-concentrating metal complexes, then of course you think, okay, the surface-seeded growth should be faster because you have a very high local concentration, and this should be prevented because the growing nanoparticles are protected by the cage. Oswald ripening will depend, I think, on the conditions, and I have no detailed information on that now. So there are already some reports on templated nanoparticle formation using DNA or polymers or MOFs, and also dendrimers have been quite popular in pre-concentrating metal complexes for nanoparticle formation, and also this organic cage has been used to protect further growth of nanoparticles. So there is some prior art in this area, obviously. So our initial approach was a covalent approach where we attached iridium complexes covalently to this ditopic ligand, and we can form the metal complex with palladium and with platinum. With palladium, we could clearly characterize the metal complex and the whole cage. With the platinum nanosphere, the NMR suggests that we have the compound, but we could not get MS data. And then we did reductive conditions to form nanoparticles, and for the palladium nanosphere, that is not stable under these conditions, so it decomposed. And the platinum nanosphere is stable, but we could not characterize. So it was a little bit complicated here. We did analyze the size of the iridium nanoparticles that was formed under these conditions. And just the iridium complex gave much larger nanoparticles than the one in the presumably formed cage, and we had about nanoparticles of this size, 1.2. So then next we went to the supramolecular pre-organization approach to form nanoparticles. And again, we used our gunidinium-based cage based on platinum that we can fully characterize, so we know what we are having, and then we combine that with iridium complexes that can be organized by sulfonate binding, as previously demonstrated. So we can upload these iridium complexes, and then under mild hydrogen conditions at 50 degrees, we reduce the iridium complex and then locally form the nanoparticle within the cage. So metal encapsulation has been established by a NMR binding titration curve, as you can see here. So up to 24 metal complexes can bind inside. We do NMR DOSI, diffusion ordered spectroscopy, to measure the size of the cage with and without the metal complex. And by mass spec, we can identify these species. So clearly, the iridium complex goes into the cage. Next, we apply reductive conditions. So this is the iridium complex in the cage, and this is after reduction. So after reduction, we see by NMR the cyclooctane that is from the cyclodioctane in line with reductive conditions, and this nanoparticle should be formed. So we subjected this to further characterization, and we looked at the structure. So we found nanoparticles with an average size of 1.8 nanometer. So for people that calculate very quickly, this is a little bit larger than expected. So these nanoclusters contain many more atoms than the 24, suggesting that during the nanoparticle formation, we still have exchange of metal complexes from one cage to the other. So clearly hydrogen bonding can lead to pre-organization, but it cannot prevent the formation of slightly larger clusters. So next we wanted to prove that the spheres are still intact, so we see still the NMR, although broadened because of the nanoparticle. We can do NMR dosi, showing that the cage is the same size as before the reduction. XPS shows that the platinum is still in the oxidation state 2, and iridium is mostly in iridium 0, although still some iridium 1 is present. And these are the HDF STEM pictures, where we show here that iridium and platinum coincide, indicating that the iridium is still in a nanoparticle. So next we did some catalysis, the hydrogenation of nitrostyrene, where we can hydrogenate the CC double bond in a nitro group. If we have our encapsulated particle, the only product that we form is the ethyl nitrobenzene, where only the alkene is hydrogenated and the nitro is untouched. And even if we leave it longer, the nitro will not be converted. If we look at the non-encapsulated particle as a reference, what we see is, we see also this product, but this is over-hydrogenated to ethyl aniline. So here you can see byproduct formation. So this reaction itself may be not so important, but clearly it shows that we can make nanoparticles inside these nano cages, and that these nanoparticles have different properties compared to the nanoparticles formed outside the cage. So next we were interested to see if we can extend it to rhodium nanoparticles. So we made a rhodium carbene analog that was also bound into these cages. And then we did reduction under reductive conditions. We formed the nanoparticle, but we found that the nanoparticle is not as stable. So the iridium nanoparticles we can keep for months in solution and they remain the same. And these type of rhodium nanoparticles, they become larger after overnight. So we thought what was happening, and what we found that these nanoparticles are so reactive that we also reduce acetonitrile as the solvent to make amines, primary amines, and follow-up reactions lead to secondary and tertiary amines. So we have byproduct formation. So yes, we can make the nanoparticle, but it is so reactive that we form byproducts. So then we thought maybe we can make rhodium-iridium alloys to tame a little bit the reactivity of the rhodium nanoparticle, but also to demonstrate that we can use our nano-sized cage to make alloys. So what we did is we took again our platinum cage with the guanidinium, and now we mix in a iridium complex with the sulfonate and the rhodium complex with the sulfonate, mix them in different ratios and do the hydrogenation, expecting to form the alloy. And we did these different ratios. And what we found from these experiments, that if the ratio is 16:8 or higher, with a larger content of iridium, the activity is tamed to such an extent that we no longer see solvent hydrogenation. And next we also looked at hydrogenation of cinnamyl aldehyde, where we can have CC or CO double bond hydrogenation leading to different products. We typically see only the aldehyde is formed, so we have selectivity for the CC double bond hydrogenation. And here we see two different experiments where we vary the iridium content, and we see the conversion of cinnamyl aldehyde after 2 hours of reaction using the alloy and using in the control a mixture of pre-prepared pure iridium with pure rhodium. So this is the pure iridium, pure rhodium, which is more or less a linear line as expected. And here you see deviation. So here you see that alloying leads to less reactive rhodium-iridium complexes. And from 16, we no longer see the reactivity of reduction of the solvent, so we no longer see byproduct. I think the most important message from this slide is that we can make also alloys by just making mixtures of different complexes. So the next step was moving towards palladium, and if we want to go to palladium, we explored a lot of different carbene complexes, and we found that we really need bidentate palladium ligated complexes to have an optimum between the stability of the palladium complex, but also reactivity towards hydrogen. So again, it's utilized with the sulfonate group, so it can be pre-organized in the cunardinium cage. And again, we need hydrogen for the reductive formation of these nanoparticles. Important note is that these type of palladium complexes need to be prepared silver-free, because if it still contains silver, we form palladium-silver alloys. Also interesting, but maybe for another time. So here is again the titration data, where we can titrate in up to 24 of these complexes in the cunardinium cage, and after that it levels off. And these are the dosy spectra, so this is the diffusion constant of the free gas complex, and in the nanosphere it overlaps with that of the nanosphere, indicating that all the gas molecules are inside. And again, we also have mass spec data to confirm that these complexes go in. So next we looked at the reduction, so the reduction of the palladium complexes that are pre-organized in the nanosphere, and as a control, just a free palladium complex. And at 10 bar of hydrogen in acetonitrile, we form this solution, suggesting that we have palladium nanoparticles, and in absence of this sphere, we see a lot of palladium precipitate, indicating that we have a completely different material. Next, we did the analysis in collaboration with the group of Petra de Jong, and now we find much larger nanoparticles. Here you can see up to 4.7 nanometer, whereas the cage diameter is about 5 nanometer. And this indicates that for palladium, apparently the whole cage is filled with nanoparticle, and further growth is just prohibited by the boundaries set by the nanoparticle. And here again, you see the surface analysis data where palladium and platinum are on top of each other in line with the nanoparticle being inside the molecular cage. So we were a little bit triggered by this larger nanoparticle. So how does this form? So we monitored the particle formation over time by electron microscopy, again in collaboration with the group of Petra de Jong. And here you see the particle diameter as function of formation time, where here we have 4% conversion, 20% conversion, 60% conversion, and 100% conversion. And from this plot you can already see that even before all the catalyst or all the complex is converted, we have a very large nanoparticle. So this is in line with a model where you have nanoparticle growth and that catalyst complexes exchange rapidly on the time scale of nanoparticle formation. So clearly there is a disadvantage of using this supramolecular interaction, I would say. So we briefly looked into catalysis. So we catalyzed this acetylene with these palladium nanoparticles to form the alkene or the overhydrogenated alkane. And here you see a few reactions where nanoparticle formation time is changed from 2 to 4 to 8 to 16. And with this, we have different sizes of nanoparticles. And here you can see after 4 hours, we have mostly the alkene and a little bit of overhydrogenation. And the nanoparticle stays the same large size, and therefore the results are the same. If you do nanoparticle formation outside the cage, then you can see you get a lot more overhydrogenation. And again, this shows that the nanoparticle inside the cage has different properties from that outside the nanosphere. Still triggered by the idea of forming nanoparticles with a precise number of atoms, we did the following experiment. So we drop casted these cages that were uploaded with these metal complexes on TEM grids, and then we did a gas phase reduction. And because the gas phase reduction doesn't allow metal complexes to change from one to the other cage, during the reduction time, we expected much smaller nanoparticles, and this is indeed what we observe. Nanoparticles of about 0.9 in line with what you would expect if you have about 24 atoms. So I think this is our lead, this is our perspective to nanoparticles with precise, atomic precision, but we need to do a lot more experiments in this area to make this sound. So in the next part of my talk, I would like to elaborate a little bit on these type of M2L4 cages that we have been exploring for various applications. And I would like to introduce it with using it as a supramolecular catalyst. So as a supramolecular catalyst, you have catalytic active sites, but you also have a binding site where you can bind gas molecules. And this binding site can be used to modulate the reactivity of this platinum source. And with that, we have a system that can respond with a sort of feedback loop. So we did gas binding studies, and these diketones, they bind quite nicely, depending on the shape. Obviously, nitrile bind, but very weakly, and also this cyclic compound does bind. And binding occurs via hydrogen bonding with the CH next to the pyridine and the carbonyl, in line with what others have reported as well. Next, we looked at the cyclization of this alkyne acid to form this 5-membered ring. We on purpose put phenyl substituents on this, because then the substrate is too large to bind in the pocket, so the reactivity is only at the outside. We studied this mechanism with kinetic isotope effect, kinetics and DFT calculations. And what we observe is we have alkyne coordination, then we have a sort of insertion into the platinum and deprotonation of the alkyne, and then we have a rate-determining proto-demethylation. So from this rate-determining metal deprotonation, we thought, okay, if we have an effector over here, then the effector can change the electronic properties of the platinum and thereby induce higher or lower reactivity. But also the effector can change the local acid concentration, and both should lead to enhanced proto-demethylation and therefore a overall higher reactivity. So we looked at these maleic acids in diprotonated and diionic states, and we did all the binding studies, as you can see here, by NMR, and that's maybe a little bit too detailed, but we proved that they bind inside. And also we looked at all the other substrates that can bind inside, and after establishing that they bind inside, we use them as effectors inside to change the reactivity of the platinum. And again, we probed the reaction of this cyclization reaction. What we found is that if you have no effector inside, then we have this reactivity 2.5, and then we can upregulate by adding these type of monoacids up to a factor of 45, and we can also downregulate by adding this benzoquinone and this dicyanobenzene. So we have a molecular cage in which we can control the reactivity by the effector that we bind inside. Next, we also did we compared the reactivity of this cyclization with the cyclization of this substrate, and we found that this is converting in higher rate, which was not according to expectation, because this substrate is pre-organized. So we thought maybe this substrate acts as its own effector. And so maybe it's bound inside, and therefore it changes the rate of the reaction of the formation of its own product. So we did a competition experiment where we looked at the single experiments and the experiments in a mix, and indeed we see that this substrate is much faster converted in the presence of this substrate, and this substrate is converted more slowly in the presence of that substrate, in line with the substrate being its own effector. It facilitates, its own reaction. So then we did an evolutionary experiment where we looked at evolution of effectors that change reactivity. So we started with this catalyst that doesn't have any effector at all, and then we have a turnover frequency of 2 per hour, cyclization. Then we add this substrate that is bound. It's known to be a cofactor to control this reaction, so reaction goes up, but it is also converted itself. So over time, this forms this cyclic compound, and this cyclic compound is completely formed after 12 hours, is again a effector. So we added more of the substrate, and now it's converted in even higher reactivity. And then over the course of 5 days, this cyclic compound is ring opened with water, forming this acid analog that is even a better effector, adding again a substrate leaded to even higher reactivities. So this shows that we have a sort of auto-regulated reactivity of our catalyst. And although this is very fundamental and new, the vision here is that we would like to develop catalysts that respond to the environment, with the vision that if you look at biomass or waste mass, that it contains a lot of components that may need a different catalytic activity. Okay. So now you are introduced into these type of molecular cages that we can make. And I promised again to bridge the gap between homogeneous and heterogeneous. So with Pieter Laner's PhD student and with Professor Jan and Rotenberg, we teamed up, and they are experts in heterogeneous catalysis, and they had a material called Vulcan, which is a carbon material that is porous. And in these pores you can bind anions. And these complexes, they are cationic and have anionic BF4 minus counterions that are bound in here. So by just adding these type of complexes, we can surface graft our cages on these Vulcan type supports. So we analyzed the surface of this, and this is in collaboration obviously, we don't have electron microscopy. But here we compare the monometallic with the bimetallic, and all the dots here are single platinum atoms, and here too. And if you zoom in, here you see a random distribution of these platinum atoms, and here you see that the platinum atoms are always coming in pairs in line with the cage being adsorbed onto the Vulcan material. Also, we did halved HDF. And here we established that if we have platinum, we also have fluor as the counterion and nitrogen based on these ligands. So all in line with surface grafted molecular complexes and molecular cages. Next, we looked into hydrolysis of ammonium borane as the model reaction for this. So you can use a catalyst for this hydrolysis, and hydrogen evolves, and in the group of Gadi Rotenberg, they developed the so-called bubble counter, and you see a sort of display of that here. And it's a very interesting machine because it counts the bubbles very accurately. And then you can calibrate these bubbles, and you can do kinetics, very precise kinetics, with this very simple machine. So as we form hydrogen, we use this bubble counter to follow kinetics. And here you see the results, so we can determine the turnover frequency as function of the temperature. So we ramp up the temperature in time. And because it's so accurate, we can have turnover frequencies as function of temperature. Vulcan is not active. The platinum 1 complex is poorly active. And then the cage is quite reactive, quite active in this hydrolysis. And then this cage that also has this amine at the inner side is the most active of all. We can use these data to make Arrhenius plots, and here we have activation energy of the monoplatinum of 21 kilocalories per mole. This cage is a little bit more active, and here we have a curved Arrhenius plot indicating that something is happening as function of temperature. And we can look at the activation energies as function of temperature. And here you see very low activation temperatures over here, and then it changes gradually. And we think that this has to do with the following. So we probably pre-organize the ammonium borane and the water inside, and this interaction with the pyridine may be a function of temperature, and therefore we see a change in Arrhenius plot. Of course, now we have this heterogeneous catalyst, and we also look at recycling studies, and here you see overlays of 3 different runs, and you see that the rates are all the same for the 3 different runs, and they all go to completion, so total turnover numbers around 40,000. So it's a really stable system that can be used over and over again. Of course, this is just an initial study, but I can imagine that you can extend that to many other different cages and many other different reactions, if you like. So with this, I would like to conclude. So with supramolecular cages, we can make well-defined nanoparticles, and these are just the beginning. I believe that we can do many more different things, and we hope to explore that in due time. We can also make smaller nano cages for effector-controlled catalysis, and these cages can easily be grafted on Vulkan, and we also looked at the larger cages, and they are grafted on Vulkan in very similar fashion. I would like to thank the people that are involved, in bold the people that were actively involved in this part of the research. Funding, I would like also to thank CBBC as a consortium that was sponsoring the project on nanoparticles, not only about the money, but also bringing in the other expertise for the characterization of these nanoparticles. With that, I would like to thank, and I would like to thank the whole group. This is a group picture of last year during group outing. And if there are any questions, I'm happy to answer.